So our next speaker is Cheuk Yu Mak from University of Sheffield. We will talk about Lagrangian torus fibrations over integral affine manifolds with Gross-Siebert type singularities.
Yes. Okay. Thank you. Thank you for the introduction and the invitation. So my talk is just, as Ilia said, it's just a continuation of this talk. Just a continuation. So I don't need to state any theorem. I just need to go to the context. So recall. We have this wedge. Okay, sorry. And then we have the corresponding compressified space. And we have a potential function. And our hypersurface. And sigmas are elements in the sigma plane. And A or tau would be elements in the delta simplex. And Ilia mentioned that in some open sets we have a nice structure we have some linearity in certain direction for the potential, so we have some nice properties. So let me say more precisely what it looks like, or maybe give some examples. So this is the pullback. Let W sigma tau to be the pullback that he wrote. So he wrote it as U tau star intersect V sigma star, which is the same as pi inverse U tau intersect with Q inverse V sigma. So he used pi as the notation. Okay, let me have to say. So he used pi for the notation of this projection, but I use pi sigma because it is related to the sigma that he mentioned. And it doesn't have to be integral. That's a very important point. And so some example. So we have already seen this example.
Did you say what Q is?
Q is the map to this one. R to K plus 1, the projection map that Ilia mentioned in his talk. So and let me just redo what he mentioned. So in here, the hypersurface will project to the wedge. So mu is the moment map. Mu is this moment map. So the hypersurface will project to something like this. And then we have so this is my delta. I have tau 0 here, tau 1 here. And you can take the corresponding U tau 0. So U tau 0 is here. And then you can take the pre-image with respect to the pi. So pi sigma is certain direction that project to the invariant direction, to the Rn direction. And you can have, so U tau 1 is here. maybe I should draw it a bit further. U tau 1 is here. And then this is pi sigma inverse U tau 1. So by construction, over these two ends, we have compatible circle actions on the hypersurface. And by integrating over the action coordinates is given by just integration of the lambda. Lambda is the Liouville form, the standard Liouville form. Some the ui d theta u plus v d theta v plus t d theta t. The action coordinate is simply the integration of lambda over the torus, or the one cycles in the torus. And so you can see directly that you can already compute the action coordinates on these circle fibers, on these circles. But this is actually the key point, and it is actually different from the image under this pi sigma. So there is some change. And if you compute the action coordinate, what you will get is you will get something. It looks the same, but it's not actually the same. So over this leg, there is a corresponding base, which is obtained by integration over lambda. And in the middle, before putting circles inside, I don't have well-defined action coordinates. But this is actually a cylinder, so you can put any circles you want, and then to glue it up. But we have a canonical way to put circles inside. So this is a one-dimensional example. And the ambient space is an annulus. Something like that. Any question? Does it make any sense?
That's the standard mu.
Yeah, the standard mu.
With respect to this symplectic.
With respect to the standard symplectic form, standard Liouville form, the symplectic coordinate is completely standard. It's just the hypersurface is in a real form, depending on the potential. And we have a decomposition of the U plane using this U tau, and we have a decomposition of the V plane using this V sigma. And I'm just illustrating an example. And more generally, slightly more generally, so you can have this so for this focus example, it's similar. So you have your delta. Your delta is still the standard one simplex. And then now the sigma, depending on the projection of pi, it will look like this. But if you look at it from the top, so if you look at it from the top, the picture will look something like this. It will look something like this. And when you project sigma to this direction, remember that there is a standard 1, coordinate here. If you project it further down, then you will get the standard thing. So this is this corresponds to sigma. This is correspond to the dual of this delta check. And what we are doing is we are cutting this focus space, kind of focus space, into a region. So this is a region corresponding to R1, and let me label this name. Label the sigma. Let me call this sigma 1, sigma 2, and this is the vertex is sigma 0. Then this region will correspond to W's tau 1, sigma 1. So I'm taking this point and this ray to get this region. But actually, I should draw it in the wedge, but the wedge is three-dimensional, so it's hard to draw. So I just project it down, and then it will look something like this. Does it make any sense? Maybe no. Question?
I don't know why we are not just drawing the moment map image like we did here. What are we doing?
So what I'm doing is I want to tell you how to compare the wedge, the boundary of the wedge, which is now equipped with an integral affine structure, and how the hypersurface looks like under certain projection to the boundary of the wedge before doing anything. So these are the regions that I will use. So these are the regions that have the nice properties with certain linearity, and the potential have certain linearity in certain position. So maybe I should say. So this is a region where, so this is the F tau 1 direction. And this is the sigma direction, sigma 1 direction. And the point is that the potential is linear in this direction, in both. That means it's all in two directions. And but all in another region, for example, in this region, the potential is only linear in this F tau 1 direction, but it will be convex in it will be it will be convex here.
So it will look like this kind of.
Yes. It's exactly. So okay. And so roughly speaking, I just use this notation to break my hypersurface into the corresponding region. And the way you should think about it is in the central region, it is just this. But when you go to this region, this is how you think, but it is not exactly. So when you go to the respective region, the equations kind of getting simpler and simpler. So in the middle, we have this KND. KDN is 101, the focus type. But over here, it will be of another type, a simpler type. And in the end, so here is the simplest. So this notation is KDN. D, if you remember, is the trivial direction. that doesn't even involve in the definition of the hypersurface. So these are some combinatoric which tells you how to read off certain certain region of your manifold and the corresponding type, corresponding local type. You can complete it yourself. So for example, this is 0, 1, 1. So and now let me explain some of the properties of my potential function.
So you take product. Take like kind of in this infinite strip region, you take a product fibration.
And that's a very good point. So this is a very good point. No, it's not a product. So smoothly a product, but symplectically not a product. That is exactly the key point of my talk. So yes. So then if you, because you have already asked, let me just say it. So we call this a pseudo-product definition. If you have an excess symplectic manifold, that means d lambda is symplectic. Okay. So we call it a pseudo-product.
But maybe Cheuk, you can mention what's the key point. It's not a product because the direction of each linear is not integral.
Yes, that's right. So so let's draw a one-dimensional higher. So this is the negative vertex. The invariant plane is the corresponding delta is this triangle. And then now the ray, the discriminant can look something like this. This ray has no reason to be integral. And then as long as it is not integral, then you cannot use a product symplectic form to achieve this discriminant. And this is exactly the f tau direction. So this is the f tau, if this h is tau.
So for a while we try to wiggle them into integral directions and wiggle them back to future.
So we call it a pseudo-product. It's a pseudo-product. There are various things. So first of all, there is a isotropic integrable distribution. D-dimensional. In the example, that distribution is precisely f tau cross sigma in n sigma tau. So it's exactly the direction you see. And moreover, there is a tk plus d action on m, and distinguish subtorus tk. And a distinguished subtorus tk in tk plus d. So in our case, the tk will be the global tk action coming from rotating the product coordinate. So we call that hypersurface, looks something like this. looks something like this in complex coordinate. But of course, as Ilia emphasized, it is not really the thing we use. But you can see that there is some TK action from here. That's the distinguished TK action. But when you pass to some other region, like here, you have more symmetry. So that's why your D will get bigger and bigger when you go to other, when your tau getting smaller and smaller. You will have more and more symmetry, and then you will have bigger and bigger torus. And and it has the nice property. So D, we call that D is the kind of the smoothly trivial direction. And in an example, so let's take this example. Let's take this example. The F tau direction correspond to the D direction. But there is no distinguished corresponding torus for this D direction. So what you can do is you can think of if you take there is this TK plus D action, we will have the corresponding moment map, and then the moment map fiber will look like the slices of focus. But there are many choices you can take. You can take some slice of this form, which correspond to certain TD action, the moment fiber of certain TD action, or you could take something of this form, some other slices. And any two different choices are given by a splitting of this exact sequence. But no matter which choice you choose, you can see that, okay, this is just a one parameter family of focus. No matter how you cut it, the slice-wise is also a focus. So you can see that this has the following property. So I should continue with that. So for any splitting, of the exact sequence and the corresponding TD action, so is the action is free, and moreover, it will induce. So let mu s be the moment map. It will induce an isomorphism from the integrable distribution to the dual of the Lie algebra. So it is this in this picture. It just means that so f tau is some vector field on M tangent to M, and then no matter which slice I choose, when I project it to this dual Lie algebra, it will be an isomorphism. And then it has three more properties. But the remaining three more properties are easier to state. So if we have a vector here, if we have a vector mu, if we have a vector, say, mu here, then by this isomorphism, I can leave the mu to be mu tilde, which possibly depends on S. Let's call it mu tilde S. The symplectic form doesn't change in that direction. And lambda is lambda mu is actually 0. And moreover, for any eta in Tk, the tangent space of the first torus, we have the corresponding induced vector field on M. And I require that the pairing between the integrable distribution, kind of goes this way. And this eta M is in the tangent torus direction. And there has to be 0. So when we have these 5 properties, we call it a pseudo-product. So I should say some example. I should mention some examples. Oh, of course, all these N-sigma tau are examples, but let me write them in more explicit form. So, trivial products. Okay, let me just write it. If M is W cross T star TD, and the integral distribution is given by cotangent fibers. And suppose there is a Tk action on W, then this will be a pseudo-product. And you can imagine that the cotangent fibers correspond to the trivial direction. And we have, in this case, there is a natural splitting of Tk plus D, but this is just a very special case. And a more interesting case is when M smoothly is still a product, but then the exact one form, the one form, the primitive of omega.
You don't want to use double.
Ah, okay. X then. X is some other symplectic manifold.
X. Not W.
Okay. So now this one form is kind of a twisted one form. Smoothly is still a product. Or here I really mean lambda M is lambda X plus lambda canonical. That is a product form, but this is not a product form. So beta is some closed one form on X. Beta is this coordinate, T is this coordinate. And this beta, if you think about the difference between these two, this beta exactly plays the role to make the integral affine, to make the discriminant of the integral affine structure not integral. And the distribution is still given by the obvious one, the dt direction. So these are just formal definition of this pseudo product. And now I need to mention the key results, the key properties, not the key results, the key properties of this pseudo product. Any questions before I move on? The key property is that if we have the slogan is that if we have such a pseudo product structure, not only we can do symplectic reduction with respect to this free torus action. The one form, the primitive, also canonically descend. So proposition for any splitting of the torus, or for any splitting, which in the picture correspond to choosing different choices of slices. And for any splitting, any moment map fiber, and the corresponding reduced space, moment map fiber of mu x, and the corresponding reduced space, there exists a canonical one form, which is the primitive of the reduced symplectic form. And we call that, in general, when you have a moment map, the action coordinates is only well defined up to shift, because that's how it is. But when you have a lambda, the action coordinate, as I said, is given by integration of one form. So this one form actually plays a key role to fix the ambiguity. And moreover, for any choice of splitting and any choice of fiber, we can descend. And it descends in a way that we have M, we can use the integrable distribution because the integrable distribution is transverse to the moment slices, because this is an isomorphism. So mu is kind of this direction. So what we can do is we can project along the new direction, project along the transversal direction to get a map from M to the moment map fiber, and then do symplectic reduction, quotient by. It has the property that it will send the Liouville flow of lambda to the Liouville flow of lambda red for any choices of S and any choice of F. It always just project canonically. But this, yeah. And one remark is, important remark is let's call this map pi, and not pi, let's call it P. So even though, so the key fact is that this one form, if you pull it back, it depends on S, depends on this choice. So there is really no natural choice of splitting of the torus, and there's no natural choice of lambda red as a one form on M. Any two different choices will pull back to different choice of lambda red, and lambda red is different from lambda. And that's it. The first thing to say.
What is
This lead to S is a splitting of the torus. So then in our case, what we can do is we can apply Evans-Murray construction in a compatible way, canonically. So what they do is if you have some excess symplectic manifold, and if you have some Lagrangian torus fibration, outside a compact set to something, B0, Lagrangian torus fibration, such that the Liouville flow preserve. The Liouville flow sends fiber to fiber. X lambda flow sends fibers to fiber. Then what you can do is you can extend.
Can you try another pen, maybe?
Okay. Then you can extend the fibration. You declare F0. Then you can extend the fibration by just simply applying requiring that all the you just apply the Liouville flow to all the fibers and declare that whatever you get is a fiber. So essentially you get a singular foliation on X, and from that you get a fibration. Then you can extend. By Liouville flow.
You must need some complexity, right? Because
you need the
vector field in the base
lesson.
should
Yes,
not
that's
look
right.
the-
Yes. You require that essentially you just require that the Liouville flow can extend is complete. At every point here, when you apply the level Liouville flow, you can hit upon B. So there is some completeness of the
How
flow.
do you get B from B0?
You don't get it actually. You get it actually. You don't get it concretely. So you just define the singular foliation to be whatever you get by throwing your fibers, and then the actual coordinates.
I don't think this is actually what they do. They actually take
Yeah,
a boundary.
they just
Yeah,
take the
I
boundary.
know
The
that they
Liouville
just,
domain as a
Yeah.
normal transversal to the Liouville domain.
yes.
Yes.
Yeah, they produce a fibration on a link. It's not on an open set.
I want to face it this way because because what we are going to do is we don't really have a we are not really choosing a link for that. So what we do is using this property, Liouville flow correspond to Liouville flow. To get a bijective correspondence between TK invariant Lagrangian torus fibration on n red compatible with the X lambda red are the same as TK plus D invariant Lagrangian torus fibration on M compatible with X lambda. Essentially what you do is, if you have a fibration from n red to something, then take a fiber of that map, and then by adding the torus coordinate, so this is a quotient map by TD, you add back the fiber TD coordinates, and then F itself is a subset in M. Then you can use the flow by this new direction. This integrable distribution will give you a direction to identify different moment map fibers essentially, and then this and to transport those fibers, those Lagrangian from one F to the other F. And using this, so the right-hand side is independent of the choice of sections. So this is independent choice of section. So this says that this kind of correspondence is actually independent of choice of sections. So what we can do is now we can run the Evans-Mobley construction inductively. So let me draw a picture. Example. Let's start with focus first. It's simple. So remember that we have this picture. So this is my tau. I have this is my delta. I have tau 1, tau 2, and then the projection of my sigma looks like this: sigma 1, sigma 2, sigma 0. And over here, in this case, we actually have a T2 action. So this is of type 0, 2, 0. So we have a T2 action on the preimage of this in my manifold. So in M tau 2 sigma 2, we have a T2 action. And then we just use the orbit of the T2 action to be my fibers, my Lagrangian fibers. And over here, you can do something similar. So the T2 action also add. And then, now, you look at this strip. You look at the strip. And you have the F tau direction. And you also have a global S1 action. The moment map of the global S1 action is precisely this. But the global, but then so this is like K equals to 1 and B equals to 1. So my torus is so remember my torus is looks like this. And then I need to choose a choice of the splitting of there is still a T2 action here. So this example is kind of cheap. So I can still use the T2 fibers.
But it's not free, that's the point. This is not free actually.
This is free.
No.
In this example.
Well, this is but okay.
But this is too, yeah, this example is dimension is too low. Yes. So we will see in next dimension the action is not free. But then and now what we can do is we can take a slice, we choose a section, and then we get the reduced space. This is my reduced space. And then we can apply okay, now we throw. Well, what we can do, so we already have torus on the right.
I don't believe it in this. I think you need something for this. I think you need
This one? Yeah.
There must like
Yeah, let me, this is not, let me erase this. Let me just erase this. Yeah, you don't need to delete this. So, because we are not really using it. So now look at the picture. Look at the picture. So now I'm telling you precisely what we are using. So now you choose a section and choose a splitting of the torus. You have a moment net fiber. And over here, I have already built a torus. And under after symplectic reduction, the torus becomes a circle on M rad. And this also has a circles on M rad. And I have told you that there is a canonical way to descend one form to there. And then now you can apply the flow, the Liouville flow, with respect to this lambda rad to get a Liouville flow on the M rad. And then you add back the circle fibers that you quotient out when you do symplectic reduction, then you get a torus. And we have a torus. And okay, now you can ask me, I do it for this slice. Then I can also do it for other slices. I can do this for parallel slices, for example. Then I can do the same thing. But I could choose a different section. I could choose a different splitting edge. I could choose something like this, right? I choose this splitting. The moment fiber will correspond to a different slice that is transversal to F tau. And then I have a torus here, which descends to a circle on M-red, and a torus descends to a circle in M-red, and then I apply the same thing, the real flow here. And even more, what we can do one more thing, which is starting from the purple. After we build the fibration on the purple, we can apply the backward real flow. I don't have a different color. We can apply the backward real flow of the global lambda to get a Lagrangian torus fibration. We starting after we build a Lagrangian torus fibration of the purple slice, we can apply the real flow to get a global fibration on this triangle. This is written in action coordinates. There is not really I'm not taking the pre-image of any map. And so you can ask whether the blue thing, the blue fibration, the purple fibration, and the orange fibration are the same fibration. And the answer is yes, because of the pseudo-product structure. They are all the same because of this, exactly because of this. They are all the same. So this allows you to run induction. And of course, this dimension is a bit, you can do a fibration for this example in many different ways. But in higher dimension, the logic is the same. So you can take say a negative vertex, and then you have certain F tau direction, and then you can choose different slices. Some slice here, and then some other slice there. And then you do the same thing, slice-wise flow along the red or along the blue, and then apply the global flow. Everything is compatible, just exactly because of this again. So, and then, yeah, it works in any dimension. So, and maybe sometime, okay. And let me talk about how we glue this thing together. Any question before that?
So for this video, so you start with one fiber and then start the process. It looked like you would.
That's right. I start with one fiber. Not go too far. Just
yeah, sure. And then, but then,
just do it here. Just do it here. You can take this. You can take another one. They are all compatible.
But then when you go around, so if you have to go around this central point, right? So isn't there some kind of global compatibility that you need?
No. So we have different pseudo-product structure in different regions. So here we have this.
I'm finding the pictures it's drawn, but now you continue to.
So here over this region we do
the same thing, okay, and then at some point you come back, and then
Just
there.
disjoint. So you give them all the big wedges, and then you're just filling in between the wedges. You're just separately doing all of these extensions.
Yeah.
Then you have to extend to the inside.
And you do the same thing.
But I don't understand something. So, but you have to make the kind of boundary of the polygon to match up, right?
No. There is no polygon here. So you can take any red dot here. Take a dot, take a dot.
Yeah.
And
they will always meet?
No. Of course, you choose a dot that match with that dot. So you choose a dot here, and then you choose a slice, and then take a dot here. And then here you can do the same thing. You have this dot, you take another dot here,
Yes.
and then choose a slice.
So, but then you continue going, and the last one, is there a matching condition?
No.
This last.
Oh, you can extend it.
It's already given at the coordinate.
Yeah. And over this entire region, I already have my T2 fibration. Only the entire
I see.
region.
I see these things. That's what I mean by this. Yes. Okay. Got it.
Yes. Any more questions? So, okay, then let me talk about grouing. So we really have a lot of controls on these local models. And we know all the parameters, all the region, all the things that go into the fibration. And now, what we do is we have a lot of data, many data, that many auxiliary choices. Go in the construction. But then what we can do, how do we interpret these choices? Intuitively, what you would like to do is, okay, I have this local model. By the way, we can also do wiggling, but I think it's given that the time, I think it is better to talk about grouing rather than wiggling. So
Nobody knows what wiggling means.
So what the outcome of our construction is that the discriminant will be strict, even though it is not necessarily integral, not as necessarily rational direction, but the discriminant will be strict because it comes from this cone construction. But then what we can do is we can add some one form. We can add some one form not close one form. Add some one form, and yeah, it doesn't make sense to you. But we can add some one form to change the symplectic form, to change the lambda, not to change the symplectic form. We can add some one form to change the lambda and keep the fibration. And this change of one form will change the symplectic form accordingly, of course. But then we are chosen in a way that the fibration will be still Lagrangian in this new symplectic structure, and that will change the Ashton coordinates of the Lagrangian torus fibration, even though the fibers are the same. But
And that will bend the straight leg.
yeah, it will bend the strict thing. Yes, it will bend the strict thing. So originally it is strict. The discriminant is strict. But then once you add something, and just like the data in my example, I have this x cross r cross s1, and then my lambda is lambda x plus t beta d theta, right? This beta, if you make it depends on the t coordinate, then you can do some bending. And so right, and then there are many choices, and to make sure that the choices in one local model can be patched to some other choices in another local model, of course we need to interpolate the data. So we kind of need a universal family to help us to interpolate the data. And what we are going to do is we call that we have this so delta is our invariant space. The span of delta is our invariant space. And then after we quotient it, then this guy will have an integral affine structure. So just for example, for the focus example, so focus example, these are the delta. If you quotient out the delta, you will get something that has an integral affine structure with no singularity. And after quotienting out the delta, then what you can do is you can define, so this is on the toric side, and then you can add back the theta coordinate to make it C star to K plus D. Okay. So B mod delta is RK plus D. So, and then what we want to do is we want to choose, instead of one potential function, we choose a B mod delta family of potential functions. Slice-wise, for each point in B mod delta, when you restrict to a point in B mod delta, it will be a potential function of the form that we explained. And then, so this is family potential. And then what you do, you define a big M. Okay, let me define a big C first. This is our Z cross Z B mod delta. Z is that C K plus 1 cross C star B plus N. We have a big M, which is the zero locus of the potential. So it's sum of E partial big phi partial A hat E inside this big Z. And then of course the action. So here this guy has a TK plus D cross TK plus D action. The second TK plus D action is simply given by rotating the torus, rotating the angle here. And the second action is free. So originally for each, when you restrict to one potential, the global torus action is this TK plus D. But after you add this guy, you have another TK plus D action. And this guy, so for position, or maybe lemma, let's say for position. So an application of Donaldson lemmas or Donaldson check again, M is symplectic. And then we apply our Lagrangian torus fibration, the Evans-Murray construction in family, and then we get a Lagrangian torus fibration. So I usually think of the Lagrangian torus fibration really is actually a Lagrangian torus singular foliation. Lagrangian singular torus foliation. We don't really define a map, we just define all the leaves. And then to something, I don't know, P, whatever. And then and we have so what we do now is inside here there is a canonical diagonal TK plus D. And if we do a symplectic reduction of this on level 0, then this is a symplectic. It's a symplectic manifold and has an induced Lagrangian torus fibration. Just descend from here. This Lagrangian torus fibration is compatible with that action and has a Lagrangian torus fibration. And the action coordinates of the fibration can be computed explicitly. let me explain. So what it looks like. So let me draw a higher dimensional example. So
Check you. Just letting you know it's 11:20.
yes.
You can go on for a
Yes. So I will have maybe 2 more minutes.
Perfect.
Okay. Thanks. So this is a positive vertex, and the delta is this direction. These are the delta is this direction, and then you have sigma. When you project from this direction, you will see my sigma, and then what is happening is so at the beginning, for a single local model, the discriminant is strict. It looks something like this, for example. But then, after using this family potential and this canonical slice reduction, it is essentially using a family of local models patched together to form our new kind of local model. And what we can do is, so this is also the same as B mod delta. So you can kind of, so it is, you should imagine this space is fully foliated by delta slices. You have a lot of delta. And then locally for each delta, it is governed by the local, so given a delta, it will give you a point here. And it has a corresponding potential at that point. And the local behavior near that delta is just given by the potential function restricted to a neighborhood of that point in B mod delta. And so what you can do is you have a family of local model patched together. And then this is another way to do victory in this case. So you can form a family of local models and then interpolating the data, and then for every delta slice, it has a corresponding potential function, and then you just wiggle. All the family. I mean, the family potential will give you a model that is locally for every delta slice is modeled by the corresponding potential, the germ of the potential function. And once we have that, and then we have to interpolate different local models, you just pass to the corresponding direction where you have a lower dimensional, where you have a simpler local model, and then you interpolate all the data that are involved in our canonical Lagrangian torus fibration for the local model. Then once you patch all the potential, all the auxiliary parameters, the Lagrangian torus fibrations are canonical after that. And then you just patch them up. And it is easier to draw, but it's hard to explain though. I don't know if, yeah, that's the end of my talk.